Okay, I'm going to be talking about problem 6.30 in this video, which was number 10 on the chapter 6B homework. This is one that's very like things that we've done in class a whole bunch of times, where you've got two things hitting each other, and we've got multiple perspectives on the same event, and we're going to figure out what happens. The difference here is that it's giving us some of our information in kind of a backhanded way. So it's going to be a little bit complex to be able to figure out exactly what's going on and understand it. So the problem says that we've got a student running an experiment with two carts hitting each other on a low friction track. In the Earth reference frame, so that's like the typical one in a laboratory, the Earth and the lab are fixed relative to each other, so it's the same reference frame. Cart 1, which has a mass of 0.36 kilograms, let me start writing things down, 0.36 kilograms, moves left to right at +1 meter per second. And the student walks along next to it at the same velocity. So we're going to have a reference frame in which everything is viewed from that student's point of view. So let's say that this table right here is the Earth reference frame before the collision. And this one is going to be the students before the collision. And then presumably we're going to figure out things about what's happening after. So we're going to do an Earth after and a student after. And we're going to have to piece this all together to figure out what's going on. Okay, so the Earth before 0.36 kilograms +1. Okay. What velocity in the Earth reference frame must cart 2 have? Okay, cart 2 has a mass of 0.12 kilograms, 0.12. And we're trying to figure out the velocity for cart 2 in this reference frame. So the velocity according to the Earth of cart 2, that's the thing we're trying to find for part A. That's our question. Okay. Fill in some other things that I know. What must it have before the collision if in the student's reference frame, okay, in the student's reference frame, that one's down here, cart 2 comes to a rest right after the collision, and cart 1 travels right to left at 0.33. Okay. All right, let's piece together what's going on here. So first, let me copy down the masses. Those are the same in every reference frame. 0.36, 0.12, 0.36, 0.12, and the total is 0.48 in every reference frame. Okay, in the student's reference frame, after the collision, cart 2 comes to a rest, and cart 2 travels from right to left at 0.33. This said the positive direction is from left to right, so that means that this is a negative 0.33. Okay, so we know what's going to happen in the student's reference frame after the collision. So we know everything about the after from one point of view, which means we can work out what's going to happen from all the other points of view as well. Okay, that's good. So let's see how we can use that information. I'm trying to find this initial velocity. Well, what's the difference between the two reference frames? So the student is moving in the same velocity as cart 1. The student walks along next to it at the same velocity, so from left to right. So that means from the student's perspective beforehand, this +1 is a 0. So that student sees cart 1 not moving, which means that student is going to see cart 2 moving with whatever that number was, -1. We'll find out what that is. So let me start filling in some more things that I know. I know that the momentum in this reference frame is 0.36. I don't know what this momentum is going to be. I know it's going to be the product of that mass times that velocity. Okay, we'll figure that out. This momentum is going to be 0. I don't know what that momentum is going to be yet until I find out what the velocity, the original velocity was. Okay. Then let's move down here. Okay, I've got 0.36 times negative 0.33. So 0.36 times negative 0.33 is negative 0.119 kilogram meters per second. And this one is 0. So the total momentum afterwards is, in this frame of reference, is negative 0.119. Okay, I think we might have a way of doing this now. If I know the total momentum after the collision in the student's reference frame, that means I also know the total momentum before the collision in the student's reference frame. It's got to be negative 0.119. There's no other way for that to work. So then that must mean that this cart has a momentum of negative 0.119 afterwards. In order for that to make sense, in order for the total momentum to still add up to the right value. So now I actually have a way directly of figuring out what this velocity needs to be in order to make the momentum be negative 0.119. So let me, for the moment, kind of like move this V2 minus 1, VE2 minus 1 to the side, because I can actually get the exact number for what the velocity is in this reference frame. Okay, so the velocity in this reference frame is whatever I need to multiply by 0.12 in order to get 0.119. So the momentum is negative 0.119. The mass, the inertia is 0.12. That means the velocity needs to be negative 0.99. So negative 0.99 in this reference frame in order for the momentum to be conserved. Okay, so from the student's perspective before, cart 2 is moving to the left at negative 0.99. That means before the collision in the Earth reference frame, how fast must that cart have been going? Let's think about this relationship. If cart 1 changed from 1 to 0 from the student's point of view, it dropped by 1. That must mean that the other cart also dropped by 1 from whatever it was to that. All right, so that means I need to go up by 1, which is plus 0.01 meters per second. So 0.01 meters per second in that reference frame. So let's try that out. What's the velocity of cart 2 in the Earth reference frame before? 0.01 meters per second. And there we go. So now we can begin to fill in more information in all the reference frame. It's going to be able to allow us to figure out the rest of this. So the next question is, what does the student measure for the momentum of the 2-cart system? Okay, so part B is asking for this value right here. That's the part B, because it's asking, what does the student think is the momentum of the whole system? Well, it's the total of the 2, and it's negative 0.119, and it's the same afterwards as well. So the student should measure, and I'm going to round that to negative 0.12. So negative 0.12 kilogram times meters per second. We got it. Okay. What does a person standing in the Earth reference frame measure for the momentum of each cart before the collision? Okay, so part C is asking about these 2 momentums right here. So part C is that and this one. So we already knew the momentum of cart 1 in the Earth reference frame was 0.36. And the momentum of cart 2 is going to be 0.12 times 0.01. It's going to be a pretty small number. So 0.12 times 0.01 is 0.0012. 0.0012. I think most likely that the significant figures on this is going to cause that to end up getting rounded off to 0, because there's 2 digits in the mass, and there's 2 digits in that velocity, and there's 2 digits in the other velocities and mass. So this one's going to end up being 0.36 and 0, which is correct within the precision of those measurements. It's actually 0.001, slightly higher than that in order for everything to be moving beforehand. Okay, so we were able to figure out all of that stuff by kind of working forwards and backwards between the different reference frames. And you can keep doing that to fill in the rest of the table if you cared to, like knowing that to get from the Earth frame to the student frame, you have to subtract 1 from the velocities. Well, that enables us to figure out what's happening in the Earth afterwards as well. You need to add 1 to the velocities. So that means this one is +1, and this one is plus 0.67. And then you can add up the momentums, and you would find that it is still conserved. You get the same value as before, which is like 0.36 right there. This is going to end up being 0.36. The energy will, the same amount of energy will disappear in both reference frames from kinetic into internal forms, and so on. Okay, so thank you, and